In this video, we're going to talk about voltaic or galvanic cells. So let's start by talking about spontaneous redox reactions. If you put a strip of solid zinc into a solution that contains copper 2 ions, the copper ions are going to accept 2 electrons from the solid zinc ions. Now this is what's going to happen when you put a zinc rod into copper 2. Now here we are placing this strip into the solution. This is going to reduce the copper ions to form solid copper, which is going to stick to the solid strip of zinc. The solid zinc atom that has lost 2 electrons or was oxidized becomes aqueous and enters into solution. And if you look at the activity series, you're going to see that zinc is more easily oxidized than copper. The zinc gets oxidized and the copper gets reduced. So voltaic cells or galvanic cells are devices in which this electron transfer occurs via an external circuit. They are spontaneous, and this occurs when our delta G is equal to 0. Now, chemical energy is going to be converted into electrical energy that's going to move electrons in these cells. So here's one picture that you may see of a cell, or voltaic cell. You have a voltmeter, you have a switch that turns it on and off. You've got your zinc anode, you've got your copper anode, and this is what we call a salt bridge, so we'll talk about that. Your cation are going to move from your anode to your cathode, and your anions are going to move from the cathode to the anode. So this is just a different picture. It uses a different salt bridge. We're using sodium sulfate here instead of sodium nitrate. But you can see, let me move this. Okay, so you can see that the oxidation reaction is taking place over here, and the reduction reaction is taking place over here at the cathode. This is what we've done here is split the 2 half reactions into 2 half cells. The galvanic cell forces the electrons to travel through a wire in order to complete the oxidation reduction process. So each half cell is going to have a solid electrode immersed in an electrolytic solution, or a solution that contains ions. The anode is the electrode where the oxidation takes place, where you lose electrons, and the cathode is the electrode where the reduction takes place, or gains reaction. So we're going to look at what happens at each of our pieces, our cathode and our anode, separately, and then we'll look at our salt bridge. So you've got your anode, which is your zinc, losing electrons, your cathode, which is your copper, gaining the electrons, and your salt bridge, which completes the electrical current. Remember that cations move from anode to cathode, anions move from cathode to anode. You have 2 solid metals that are the cathode and the anode. Now there are a few rules. So at the anode, the electrons are going to be products. This is your oxidation. At the cathode, the electrons are reactants, which is reduction. And remember that electrons cannot swim. So we will talk about that a little bit later. So electrons are going to flow from anode to cathode. So the anode is negative and the cathode is positive. Electrons cannot flow through the solution. They don't swim. They have to go through a wire. So here's a way to help you remember Leo A. Gerke. The loss of electrons is oxidation at the anode. Gain of electrons is reduction at the cathode. You can also remember. Now here we're looking at what happens at the anode and at the cathode. So as the reaction proceeds, the mass of the anode is constantly decreasing and the mass of the cathode is constantly increasing. The oxidation occurs at the anode, reduction occurs at the cathode. Okay, so your zinc metal is going to lose 2 electrons as a solid zinc atom becomes aqueous, zinc plus 2. Those electrons are going to travel through the anode, or they're going to travel to the anode through the wire and into the copper cathode. The electrons arrive at the copper electrode. Your copper 2 ion in solution is going to accept them and turn into solid copper atom that's going to plate on the cathode. As this reaction continues, remember the mass of the anode is decreasing and the mass of the cathode is increasing. Okay, so anions and cations are going to move through this porous barrier, the salt bridge. So the cations move into the cathodic compartment to neutralize excess negatively charged ions. So your cathode is copper plus 2. Your electrons need to go in there. The counter ion of copper is in excess. The anions move into the anodic compartment, not a funny word, to neutralize the excess zinc that's formed by oxidation. So let's talk about this salt bridge. It's a U-shaped tube that contains a solution of gel with soluble ions. So sodium, sulfate, nitrate are commonly used. These ions are not going to play a role in redox. The ions from the salt bridge must not react with ions in the electrolytic solutions to form a precipitant. For that reason, we don't use chlorides a lot. Ions from the salt bridge are going to keep solutions in the half cells neutral, and the solutions do not remain neutral. If they don't remain neutral, then your reaction will stop. Okay, so the solutions have to remain electrically neutral for the reaction to continue. This is the purpose of your salt bridge. All right, and the battery will die when there's no more solid zinc at the anode, if we're using our above example, or when the reduction half reaction runs out of copper. Alright, so here is what's going on in the salt bridge. So the sulfate ions are moving into and out of the salt bridge to maintain neutrality. So as your zinc plus 2 enters the oxidation half cell, a sulfate also enters the oxidation half cell to maintain neutrality. At the same time, your copper 2 gains 2 electrons and forms solid copper. To keep the reduction half cell neutral, a sulfate ion has to leave the solution and enter the salt bridge. If the sulfate did not leave the solution, there would be excess negative charge and incoming electrons would be repelled. This would cause your reaction to stop. Now the salt bridge itself remains neutral because the sulfate left to enter the oxidation half cell at the same time that the sulfate from the reduction entered the salt bridge. Now this next one's going to show some movement. The zinc ion is moving into the salt bridge and 2 sodium ions are moving out of the salt bridge to maintain neutrality. So as the zinc 2 entered the oxidation half cell, a zinc ion entered the salt bridge to maintain neutrality. At the same time, the copper 2 gained 2 electrons and transforms into a copper solid. This would have given the reduction half cell an overall negative charge, except for the fact that 2 sodium ions left the salt bridge and entered the reduction half cell. The salt bridge itself does remain neutral. It would have gained an overall charge of plus 2 when the zinc plus 2 ion entered from the anode, but 2 sodium ions, which are positive charge, left the salt bridge to enter the cathode at the same moment. If everything does not remain neutral, the electrons stop flowing, and if the sodium ions did not enter solution, the cathode would not have an overall negative charge and the electrons would be repelled. Remember that cations always move toward the cathode in the salt bridge.